gentlemen, we have a treat this morning. Nima is going to be talking to us about log-concave polynomials and using them to solve discrete optimization.
Thank you. So this is joint work with lots of lovely people. So a lot of the talks in this workshop are about continuous optimization problems and using hyperbolic polynomials to solve that. This is not one of them. So instead, we are going to solve discrete optimization problems, so things of this form. So you have a function on subsets of size k of n elements, and you want to maximize this function. So this is a very generic one. But polynomials are going to show up, and the way polynomials are going to show up are you should think of this function as encoding the coefficients of a polynomial, and we are going to use this polynomial and its properties to basically do this discrete optimization problem. Okay. So just to make sure we are all on the same page, for each subset of size k, you just form a monomial out of the n variables, and the value of the function just gives you the coefficient of that monomial in the polynomial. So there is one very specific example of discrete optimization that's going to show up a lot in this talk, and that's when this function is given by a determinant. Okay? So think of n vectors that are in some Euclidean space, and you're assigning to every subset of size k of them the value, the determinant of, or the volume spanned by the vectors in that subset squared. Okay. So as many people here probably know, these are the coefficients of a very useful polynomial. It's a determinantal polynomial. So basically, the associated polynomial to this discrete function is easy to compute, basically. That's what I'm saying. So if you form the gram matrix of these vectors, so this is an n by n matrix, where in entry ij, basically you write down vi dot vj. What you're basically trying to compute when trying to compute g mu is the sum of k by k minors of this matrix. Every k by k minor, basically its determinant gives you the volume squared of the corresponding vectors in that subset, and you're trying to compute the sum of the k by k minors, which is the elementary symmetric polynomial applied to the eigenvalues of this matrix. So the polynomial in this case is easy to compute, but can we use that polynomial to do discrete optimization? That's the question. So this was done by Nikolov in 2014. So what he showed was that we can find a subset of size k that maximizes this determinant up to a factor of 2 to the k. And this is also known to be the best approximation possible, assuming complexity theory assumptions. So you might think that this is actually a terrible approximation factor, but you should think of the determinant as like a degree k function, and so this is the right sort of approximation. Any questions so far? Feel free to interrupt at any point. Okay, so what I'm going to show you is next is basically a generalization of this to arbitrary functions whenever the corresponding polynomial has a certain property. So if you want to find the maximum coefficient of this polynomial, here is an integer program you can write that solves the problem for you. You just plug in 0, 1 numbers for the variables in the polynomial, and you make sure that exactly k of these variables are 1, and this gives you the value of the polynomial at this point gives you the coefficient of that k variables. So as is usual in approximation algorithms, we're just going to relax this to a non-integer program. So we're just going to drop the constraint that these are 0, 1 variables. Instead, we're just going to make sure that these are positive numbers. Okay. This is essentially what Nikolov has also done. And now the question is this relaxation a good approximation? And more fundamentally, can we actually solve this relaxation? Okay? Because the objective here is a polynomial. It's not obvious immediately that we can optimize this.
Do you want them bounded above by 1?
Sorry?
Do you want them bounded above?
Not necessarily. It's not going to, I mean, you can put in more constraints if you want, but it's not going to be necessary. Okay. So, all right. So the first question is this approximation good? And when is it good? What properties of the polynomial implies that this is a good approximation? And the answer is that you don't actually need much for this to be a good approximation. Okay? No matter what the polynomial is, the solution to this relaxation is always a good approximation. Okay? And this is very easy to see. Basically, what you can do is you can solve this relaxed problem. You get a bunch of zi's, and then you can sample a set of size k with probability proportional to the product of zi's. Okay? So if you do this randomized algorithm, the expected value of mu at the set that you get is going to be basically the value of the polynomial divided by the normalizing constant in this proportionality. Okay. And the normalizing constant in this proportionality is just the elementary symmetric polynomial applied at the zi's. So basically, this is the value that you try to optimize from the relaxation, and this divided by the elementary symmetric polynomial is what you're going to get out of this algorithm. So the approximation factor is bounded by how much this can be. Okay? And the elementary symmetric polynomial of a bunch of variables that sum up to k is going to be at most e to the k. So an easy way to see this is that the elementary symmetric polynomial is actually a log-concave function. It is hyperbolic, for example. And it is also symmetric with respect to the variable zi. So its maximizer is going to be a multiple of the L1s. Okay? So this is maximized. So ek is maximized at basically zi is equal to k over n. And for zi is equal to k over n, ek is basically this. K over n divided to the power k times n choose k. And you can use any inequality that you want, like the fact that the n choose k can be bounded from above by n e over k times k, n e over k to the power k, and then you get it. So there are multiple other ways of getting this. You can use the fact that these are the elementary symmetric polynomials are ultra log-concave in terms of k and so on. But it doesn't matter. So okay, so e to the k is what you get. Using complexity theory assumptions, we know that at least for the determinant case, you can't get anything better than this, at least up to a constant factor in front of k. So the approximation is always good. So the question is now, can we actually compute the solution to this relaxation? And you know, we are trying to solve some optimization problem, some continuous optimization problem now. And obviously, if we have some form of convexity, we can solve it. Otherwise, we probably can't hope for such a. So in particular, what we need is at least quasi-concavity of this polynomial. Okay? We need the level sets of this polynomial to be convex. That implies that, for example, the optimizer is unique. And if you do like gradient descent or something like that, then you will converge to it. So quasi-concavity is just this fact that when you basically take the contour plot of your polynomial, so these are the level sets of your polynomial, g equals 1, g equals 2, g equals 3, and so on. The above sets of these sets are just convex shapes. Okay? But you know, it's a folklore fact that quasi-concavity for homogeneous things is the same as log-concavity, is the same as all sorts of other concavity. So we can hope to do this optimization exactly when our polynomial is log-concave. So when we are dealing with a log-concave polynomial, we can solve this relaxation, and it will give us a good approximation, and that's maybe the end of the story. There is one question I haven't answered yet, which is how do we even compute this polynomial? So in the determinant case, I showed you that you can compute this polynomial by forming that gram matrix and computing the eigenvalues and the elementary symmetric polynomial of the eigenvalues and so on. But in general, because we are only dealing with the case where the polynomial is log-concave, we can approximately compute the polynomial, even if we only have an oracle that computes mu for us instead of the polynomial. So this is because you can basically sample a set S with probability proportional to the term corresponding to S in the polynomial. So this is our recent result with Liu, Oiskaren, and Cynthia. And then you can use all sorts of classic reductions from approximate counting to sampling to compute the partition function of the sampling, which is the polynomial. And then you might ask, okay, so this gives us an approximate solution, but approximate evaluation of a function is enough for optimization, at least in this case. So this is all very easy and simple. But notice that what we did was we tried to basically solve a discrete optimization problem. And we reduced that basically to a counting problem. So basically computation of an expectation. And then we basically substituted this expectation with a surrogate, which was an approximate surrogate that was log-concave. And then we basically optimized this surrogate instead of the original optimization problem. So then the question is now, okay, so when we are dealing with a discrete function whose polynomial is log-concave, this all works, but can you go beyond this? Okay. So what I'm going to show you is a special case. There are things more general than this that you can do, but for simplicity, we are going to focus on this specific problem. Think of constrained optimization now. Okay, so instead of optimizing this mu function over all sets of size k, we are given a family of all of these subsets, and we want to maximize over this family. Okay. So if you think of basically the indicator function of this family as the function nu, which maps sets in the family to 1 and sets outside of the family to 0, then this optimization problem is basically equivalent to maximizing the product of mu and nu. Right? So the unfortunate thing is, even if mu and nu both satisfy what we required before, which was log-concavity of the corresponding polynomial, this product doesn't necessarily have this property. Okay? So we can't just take mu and nu, which are log-concave, and hope that the same method works for mu times. But we can still basically try to apply the same framework of going from this discrete optimization to computing an approximate surrogate of the partition function or the polynomial. And that's what we're going to do for the rest of the talk. So our goal now is to basically compute an approximation to the polynomial corresponding to mu times nu. And then hopefully that approximation will turn out to be log-concave in the variables of this polynomial. So a little bit of history of this. So Mohit and Nikolov basically did this when nu, the constraint function was coming from a partition matroid, and mu, the polynomial for mu was satisfied some stronger form of log concavity, real stability. So this was based on earlier results of Gurwitz. Then together with Cheyenne, we showed that you can still get the same sort of surrogate approximation when the polynomials for mu and nu both satisfy a stronger form of log concavity called real stability. And Strasek and Vishnoi also obtained a similar independent result. But what I want to show you today is that you don't need real stability when mu and nu, their polynomials are both log concave, you still get the same sort of approximate surrogate. And this approximate surrogate is going to end up being log concave. So this is the task that we want to do, right? So this is an expectation with variables t. I've replaced the variables to ti's. So we want to sum over all subsets S, mu of S times nu of S times the product of ti's. Okay? So at the end of the day, if we get a surrogate for this, which is log concave in terms of ti's, we can do exactly the same thing that we did before. We can optimize over ti's, and then the end result is going to be a good approximation. So to get this surrogate approximation, we have to do some tricks. So first of all, we are going to form basically the complement of this new constraint set. So nu was basically an indicator function over subsets of size k. You can form this complement function which maps, which takes basically the complement of all of the sets indicated by nu. Okay? So these are subsets of size n minus k. And so a trivial fact is that, not so trivial if you don't know what matroids are, but so basically when nu has this log concavity property, the sets defined by nu form the basis of a matroid. And now the sets defined by nu complement also form the basis of a matroid, the dual matroid. So when nu has this log concavity property, the nu complement also has this log concavity property. So the polynomial for nu complement is log concave. Okay. And now we can form this partition function that we are desperate to approximate using this the polynomial for nu complement. Okay, so let me parse this for you. So don't forget about this denominator and these divisions by ti's for now. Okay. So what I'm doing is I'm multiplying the polynomial for mu by the polynomial for nu complement. Okay. And I'm applying a bunch of differential operators to it. So in this differential operator, for each variable, I have basically partial yi plus partial zi, where yi is the variable appearing in mu and zi is the variable appearing in nu complement. Okay? So if you want to compute the right-hand side of this, what you can do is you can, from each one of these parentheses, you have to choose either partial yi or partial zi. And for any choice that you make, you can just expand this out and see what's the number that you get. And the result is just the sum of all of these numbers. Okay? Now these choices have a meaning. Basically, the set S is going to be so for every choice of partial yi's versus partial zi's that you take, I can form this set S, which is the set of partial yi's, the set of indices at which I took partial yi, right? So now when you expand this out, the partial yi's are only applied to g mu. Right? So when basically so now you're basically applying this operator. So this first part of the operator is applying, so this is the sum over all s. This is exactly the same expression as on the right-hand side. So when you apply this operator to g mu times g nu, the partial yi's get absorbed by g mu. Okay? And what you get out of this is the sum over s. So this expression is going to be mu of s. Okay? Because you're taking derivatives with respect to the variables yi's. And this is going to end up being mu of s. This is going to be a 0-1 function. And it's going to be exactly nu complement of basically s complement.
You need to evaluate at 0.
So you actually don't need to evaluate it at 0 because the end result that you get is a constant. So the degrees match up. So the degree of this thing is k, the degree of this thing is n minus k, and I'm applying n partial derivative operators. So at the end I don't need to take the variables to 0. Okay, so by definition this is the same as basically nu of s. And I get what I wanted. Okay. Now the t's also work out. So for that part you can just leave me or you can just see. So why did we go through all of this trouble? The reason we went through all of this trouble was that whenever you have a bunch of partial operators applied to a polynomial, you can form a thing called a capacity inequality. So this is basically a generalization of results proved by Gurwitz first and generalized in various ways using very clever machinery. So the thing that we wrote our partition function as, which was something of this form, a bunch of partial operators applied to a log-concave polynomial, you can lower bound it by an optimization problem, by the result of an optimization problem. Okay. So I gave a talk about this in the previous workshop. You can just go see the details of that for the proof. But for now, just believe this. So this is basically based on some intuitions about entropy and so on. But the end result is that to approximate this value of the polynomial for mu times nu, what you can do is you can solve this optimization problem, and the result is an e to the k approximation. So, so what is this optimization problem? This optimization problem involves the polynomials g mu and g nu complement. There is this funny p-value that's outside. This p-value, you can think of it as sort of like a marginal. Okay? So think of choosing a set S according to mu of S times nu of S. And this P would be the probability that the element I would be inside the set S that you selected. So for exactly for the exact marginals, this gives you an upper bound. And for any other value of P, this up to an e to the k factor gives you a lower bound. Okay, so all right, so we've basically come up with a surrogate for this partition function that we were interested in. That's the punchline. But why is this surrogate good? Why is this log-concave in the variables t? So this is again a trick that you can basically Gurwitz came up with. What you can do is you can absorb this P into the polynomials. So what I've done here is there is a P to the P here. You can basically absorb this into the denominator, and that becomes this thing. All I've done so far is just move the p to the denominator here. But now, since I'm doing an optimization over variables y and z, I can replace the variable y by basically, I can let y prime be y over p. So if you do that, then this becomes y prime. And here you get p times y prime. Nothing crazy so far. But then for any fixed value of y, this thing is log-concave in p. Right? G mu of p times some constant is log-concave in p, because G mu was log-concave in p. Now when you're doing basically, now once you do an infimum over a bunch of log-concave functions, you still get a log-concave functions. So you can also solve this maximization problem on the outside. Okay? You can do the same trick for t. Basically, if you multiply the variables t1 up to tn to the right-hand side of this, you get g nu complement of z over t times t1 up to tn. And this thing is log-concave in terms of ti's. Because this is basically g nu of t over z times a bunch of z's. So for any fixed value of z, this thing is log-concave in terms of ti's. And once you do an infimum over a bunch of log-concave functions, you still get something that is log-concave in terms of ti's. So the end result is a surrogate for our partition function, which is log-concave in terms of ti's. Any questions so far? Yeah.
So can you get it to work when nu is not a 0-1 variable?
So everything works as long as nu complement is basically, so as long as both nu and nu complement give you log-concave polynomials.
Yeah.
Yes.
But if it does not, so in general it does
So we don't know. So for real stable things, this works, this flipping works, but for log-concave, this doesn't work necessarily.
You can still save it,
Yeah, but I don't know a way currently. Yes. So that's a, so I cheated a little bit here. So I assumed that this nu function was a 0-1 valued function, which means that nu was giving a matroid constraint on our optimization problem. So what Peter was saying was, okay, so for 0-1 valued functions, we know that this complementation operator preserves log-concavity. This complementation operator also preserves log-concavity when you have some stronger condition called rail stability. But when you only knew that when you only know that nu is log-concave, this doesn't necessarily hold. Okay? So for non-0-1 valued functions, nu complement is not necessarily log-concave when you start with a log-concave function. So for that case, you could still possibly try to do an optimization like this and hope that it gives you the correct approximation, but we don't know currently. So, all right, so this is all good for solving the determinant optimization problem under a matroid constraint. But I want to show you in the rest of the talk another application of this. Okay. So this is Nash welfare optimization. I think in one of the workshops we had a talk about this, but let me just go over it again. So this is an optimization problem coming from economics, where you have a bunch of items that you want to allocate to a set of people. So these people, there are n persons, they have utilities for these items. And their utilities are additive, meaning that when they get two items, their total utility would be the sum of the utilities for the individual items. Okay? So there's a lot of debate about how you should allocate these items to people. And there are generally many criteria that people study. So one of them is, for example, maximize the sum of the total utility, or this is called the regular welfare. So this is an easy problem. You just assign each item to the person who appreciates it the most. There is also a variant where you want to maximize the minimum utility of every person. That's trying to be like fair. This is called the Santa Claus problem, and it's generally very difficult. There is also a middle ground called Nash social welfare, where you try to maximize the geometric mean of the utilities of the people. So this is like the zero norm of the utilities. This is like the one norm. This is like the negative infinity norm. This is like the one norm. This is like a zero norm. So for this problem, let me just, there's been a lot of work on this problem, but let me just mention the most recent one, which gives you an e to the 1 over e approximation. Okay? But what I want to show you is a worse approximation factor. It's still going to be a constant, but it's going to be using this machinery. Okay? So first of all, the first time that you see this problem, the thing that you might try is to write down basically a regular relaxation for it. Okay? So you basically put down a variable xij, which says whether you allocated item j to person I. And you try to maximize the product of the sum of the fractional utilities assigned to each person. Okay. So there is only one constraint, that each item should be assigned a total of 1 time. And you can actually solve this relaxation because the objective here is a polynomial that's log-concave. So when you take its log, it becomes a concave function. You can optimize it and so on. Everything works. But the problem is that there are actually examples where this relaxation is very far off from the actual optimal solution that you can possibly get. So think of basically an item which is very highly valued. So like, let's say this sweater is like loved by everybody. So what the fractional solution can do is it can cheat and get like a third of the sweater to this person, a third to this person, and a third to this person. And now the product of the utilities would be something non-zero or very high. But an actual solution would have to allocate this sweater to only one person. Okay? So if, let's say, the rest of the items have a utility of 0, the optimal solution would be 0, whereas the fractional solution would be non-zero. So the thing that's causing this problem is that we're not taking into account the fact that each item has to be allocated exactly once. So let me erase this part. So even though this relaxation doesn't work, there is still hope to save it. We are still going to basically replace this objective with a suitable surrogate, which is still log-concave in terms of xij's. But we are going to make sure that this log-concave surrogate that we put in is always a good approximation to the actual optimal solution. Okay? So the way we are going to do that is again by running a randomized algorithm and computing its expectation, and then coming up with a surrogate for that expectation. Okay? So the algorithm, so assume that you've solved this. So forget about the fact that this is a bad relaxation. Let's say that somebody has given you a bunch of fractional values xij's. So one thing that's very natural to try is to round this fractional solution to an actual solution according to the xij's. And that means basically for each item j, you allocate it to the person I with probability xij. So for each item j, basically independently do this. Okay. So if the sweater was divided into thirds between the people, you just come up with a random number between 1 and 3 and allocated the sweater to the person whose random number came up. Okay. So if you do this, there is an expected value that you get at the end. Okay, so the expected value that you get at the end would be something like the product of the sum of, let's call them capital Xij, Uij, where Xij is basically the indicator variable of whether you allocated item j to person I. Okay. So the reason this relaxation is not good is that this expectation is not equal to that. Okay. You can't just take the expectations inside and just replace xij's by their expectation, which is xij. Okay. But what you can do is you can compute this expectation. So this expectation, so this product is over persons. This sum is over items. So if you expand out this product, what you get is a sum over basically all functions from n to n. The product of I equals 1 to n, sum I and sigma I. This is still the same expression. I've just expanded out the product over the sum. From each of these sums, I have to select one index j, and I'm just representing that choice by sigma of I. And now now once you have a sum, you can take the expectation inside, and you can just for each individual product see whether or not what the expectation is. Okay. So the point is, if sigma is injective, the expectation, you can take it inside, and the expectation would be So the point is that if for each person you chose a different item, then the expected value that you took this assignment of items to people is exactly the product of the fractional values. If, however, you selected the same item for 2 different people, there is no way that the assignment could be coming out of this. Okay? So the expectation is 0. Right? So now what we are dealing with is very similar to before. The expectation of this algorithm is basically a sum of product of 2 partition functions. A partition function of a product. So now if I define mu from n times n So now I can define basically functions over a ground set of pairs of items and people. So this is n times m. And I'm choosing just subsets of n of these things. Okay. So I'm taking this to be isomorphic to basically n times m pairs of people and item. Okay. And I'm just looking at all subsets of size n, where where I've sorry, yeah. So what nu is going to do for me is it's going to enforce this constraint that so nu of S, a subset of people and items, is going to enforce this constraint that in my set S, I'm going to look at only, I'm going to only look at sets where no item is allocated more than once to more than one people. And what mu is going to do is it's going to basically capture the utilities plus the fact that no person is allocated more than one item. So it's going to be basically the product of utilities of So mu is going to basically give me the coefficients of this polynomial. If you expand out this polynomial in this objective function, mu is going to give me the coefficients of this polynomial. And mu is going to enforce this additional constraint that I should zero out the terms corresponding to allocations which are giving an item to two people. So now basically the sum of nu s, sorry, this should also be times nu s. This thing is the expectation of my algorithm. Now mu of s is a log-concave polynomial because it's just a product of linear things. Nu of s is actually a matroid constraint. Okay? So you can actually write it as an elementary symmetric polynomial. So think of basically variables zij and then nu of basic g nu of zij's would be dn of z11 up to z So if you expand out the elementary symmetric polynomial of degree n out of these sums, I'm just looking at basically products of n terms out of these m terms. That corresponds to selecting n different items out of the m different items. And when I expand out the product from each sum, I'm selecting basically an assignment of that item to each person. So this is also a log-concave polynomial. So the same framework basically applies, and now you get a surrogate for the partition function of g of mu times nu. And this surrogate function is going to be also log-concave in terms of xij's. Okay. So you can do the same maximization trick as before, and you can solve the optimization. Okay. So the degree of the polynomials nu and mu here are n. So you get an e to the n approximation. An e to the n approximation to the product is the same as an e approximation to the geometric mean.
So where are you using that the utilities are linear or additive?
Well, to form this polynomial, I have to do this, right? I mean, if you're dealing with complicated functions, like, I don't know, submodular functions of utilities and so on, you don't even get polynomials. So there are some extensions of this to nonlinear things. There are things like budget additive and SPLC utilities and so on, where you still do get some polynomials, but let me not get into that. So I'm running out of time, so let me just finish up and mention some open questions. So, okay, so in the first part, I showed you that when we have access to this mu function, and we are doing a discrete optimization over this discrete function, we can do a random walk to do sampling and to compute the polynomial. And using that computation of the polynomial, we can get a 2 to the O of k approximation. Okay? But it's very weird because we shouldn't need access, we shouldn't need basically random walks or things of that sort. You can do like local search algorithms or things like that. So all we know for those is if you do, for example, local search on mu, the factor that you are going to get is like k to the k when you're doing the summing up maximization, for example. So it's an open question whether you can get the same approximation factor deterministically. So one other thing is, in all of this approximation, when we computed the surrogate for the polynomial for mu times nu, we ended up approximating the maximum of this function, but we never actually showed how to output a solution, how to output a set that achieves that guarantee. Okay? So that's not a problem when you're dealing with a single function mu, because then you can do method of conditional expectations and actually output a solution. But for mu times nu, we don't know how to compute the partition function exactly or enough, well enough approximately. So it's still unclear whether we can output a solution as well or not. We can output the we can output an estimate of what the maximum is, but not the solutions. Thanks.
Any questions?
So for just the cardinality constraint, initially when you like outlined Sasho's approach to get e to the k approximation, so of course there are really two parameters. One is the size that you're choosing, which is k.
Yeah.
But you also like had this vectors inherently, right, for which you're looking at a determinant.
Right.
But they could be sitting in a different dimension.
Right. So that dimension doesn't appear. So if the dimension is higher than the set that you're selecting, in this approximation factor, you don't see the dimension at all. There are generalizations for when you are selecting more vectors than the dimension, and then you have to define what the volume means. But in those cases, you can actually get much better results using your results and I think Z1s and so on. So yeah, Z1.
Okay, I guess we will reconvene in 10 minutes.